Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about a top DIY science project. So let's dive deep into it. Now, I got a lot of requests to do other than computers DIY projects because that playlist was getting a lot of attention. So this is scientific ones. Now, let us be very clear. It applies, the same rule applies. Whatever it is on sale, it's just not meeting your requirement. Like there could be many things. For example, you're like, I want this, but the cost is just stupid. It's just like, no, no. So in those sort of scenario, what else you gonna do? Or whatever you are getting, like so let's just say cheap Chinesium equipment, they are just too unreliable. Basically, they may be causing you so much issues and harm. It's like saving money is no longer viable. It's actually hurting you. So there could be many reasons where you're just like, you know what? I gotta go Tony Stark. I have to build it in a cave. So fundamentally, now what kind of people do this? Well, the people generally have a mix of touch of, so to say, a bit of madness and a bit of genius. It's not a normal thing to do. Hell, no, it's not an average thing to do. So it does require a bit of a edge on both sides. So only then you can do that. And that the fact that you can start the project, that happens if you have that bit of madness and bit of genius. But the fact that you can finish it, that happens because you have turbo grit and patience. If you lack this part, the turbo grit is like, I'm gonna do this. I'm gonna keep doing this, no matter how many days it takes, no matter how many years it takes. If you have that grit and patience to see it through, only then, let that be very clear, only then you can get into this. Only then you can go Thanos and it's like, fine, I'll do it myself. If you do not have these things, you would be ludicrously disappointed, so to say. So let's start with the first project every Tom, Dick and Harry builds is linear bench power supply. Now, here's the deal. Everything starts with power. Duh. Like you are working with LED, you need power. You're working with microcontrollers, you need power. You're working with radio, you need power. So fundamentally, everything starts with lab power. Now, what does it mean to be lab power? You can't just buy a, let's say, a laptop adapter or a 12 volt adapter, 9 volt adapter, things of that nature. No, generally, whenever you're talking about something like this, you're talking about something that gives you control over two vectors. Vector number one, voltage, meaning it's not like 12 volt, 6 volt or something like that. It's like, no, you have the range, like full analog range you have. So you can be like 7.5 volts. You could be like 7.97 volt. You can go YOLO on it. And then you have current limit. Now that is the most critical aspect. You could be like, hey, I only deal with 12 volt LEDs and I have 12 volt adapter. I'm good. No, the reason is if let's say you are working on a board and you have some sort of control system or fuse or whatever have you, those systems have to work, right? And what happens if they do not work? Well, you fry your system. But again, you are testing and you're developing. You do not want to fry your system. Current limit helps you in that regard. For example, let's say you have a system for, you must have been like, this is my fan controller system that I'm building. So this is a 12 volt cob. Now there are many 12 volt cobs. And if you look into LEDs, you will find this weird thing. They're not focused on voltage. They're like, yeah, operating voltage is like giant range. It's like especially some big cops, they could be like, oh, it starts working at 32 volts and keeps working at 52 volts. I'm like, what the hell? So voltage ranges are you, but here's the deal. They are very specific about one thing: current. Why is that? Here's the deal. When you have current control, you basically have a monitor that keeps monitoring how much current is going there. And how does it quote unquote control it? It simply drops the voltage. Now, depending on your design, your system could be like, hey, I'm gonna keep dropping the voltage until I stabilize, or I could just trip. Depending on your system. If you're working with sensitive system, you'll be like, bro, trip. Do not just like slow cook my system. If you're like, hey, something wrong happened, and let's say you set the limit to 300 milliamps. Cool. It started to draw more than that. It's like, kapat. Nope. It just nopes it. There is no power. So whenever somebody talking about current control, all it means is just dropping the voltage the moment you hit the current limit. So for example, in these sort of cob LEDs, I could set it to 20 milliamps. And the moment they start to heat up the current, because again, current is basically related to resistance. Resistance is related to temperature. The more it heats up, the more current it starts to draw. The system is like, whoa, 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 whoa. Thou shall only eat 20 milliamps. It will start to dropping your voltage. And that's why LEDs are always rated in sort of current. You need to have current control power supply, otherwise you can't test it reliably. And again, that's the easiest way to figure out like how quickly does the LED heats up. Is the easiest way. Basically, set it current control, keep measuring every 5 minutes, and it's like, okay. Quality LEDs, let's say really good COPs itself, they can handle much higher current for much longer duration, as in like full voltage. Then it will start to drop. Cheap one will drop very quickly because it heats up too quickly. So all those things require you to have a system that has current limit. Now, how do you actually do current limit? You generally have a IC like this where you have LM317. No, this is not LM317. Where the heck is LM317? Yeah. yeah, you have something like this. This is the voltage system, but here's the current control simply means voltage control. So you have a shunt resistor there. For example, in this design, you have a 100 milliohm shunt resistor. So voltage drop will happen there. Cool, awesome. You know the resistance. You know the R aspect of it. You will get the voltage. You will measure the voltage drop. Cool, awesome. That will give you V equal IR. So cool, awesome. You figured it out. But here's the signal is too weak. And what the hell you gonna do with a voltage drop? You take the voltage drop, you send it through a op amp. You increase the gain. Basically, you take the let's say 1 microvolt, you stretch it to millivolts or something like that. Whatever have you, you can set the gain, and then that gain goes to another op amp, and that op amp is acting as a comparator. It's just on off switch. And in this sort of design, you will have another source. Let's say your small voltage source, so to say. That source will give it power. Benefit of that is you have a second knob that is controlling it. So the moment this happens, this goes no, and it short circuits it. Basically, it drains all the voltage out of it. And this system can respond very quickly. Or this is another aspect of it. You might be like, why can't I just build SMPS, or shouldn't I buy cheap Chinesium SMPS? Many SMPS are very horrifyingly slow, meaning you can only see them if you have let's say oscilloscope, but you would be shocked how many of them, like, they say constant current and they have constant current, it's just slow, meaning they can take few milliseconds, and they, during that short circuit, they will dump a lot of current also. So it's not just like, okay, 5 volt, there is more current to draw, so it's a little bit more current, then it's like no, it's like full current draw. So that's why you generally do not want to have that as a starting out. Once you have experienced it, when you can know these sort of things and remove them from your design, then you're like, go you'll on it, but not as a starter. Thou shall never touch those things as starter. You'd be shocked how horrendous majority of the cheap switch mode power supply that you have on the market is. Like, they're horrible. Like, they will make sure they will fry your system. And another aspect is noise, and noise can introduce messiness. For example, ESP32 has analog to digital converter inbuilt into it. Cool, awesome. But here's the deal, that requires quality voltage. If noisy signal goes into that, it will create a noisy output. So how do we solve this? Well, we have here, this is a 5 volt switching regulator. But okay, I said this puppy is supposed to require clean. Well, I feed 12 volt in. 12 volt gets stepped down by a buck converter to 5 volt. 5 volt goes into this board, dev board. This dev board has an onboard regulator. Regulator is like this, linear regulator. It drops it down to 3.3 volt. Now the voltage is stable, it's clean, it's trustworthy. So all the system works. So this is the core aspect that you must stay away from switching system. And switching is not something that you want to have in your ecosystem before you are like, okay, how the hell all these things are working. Like, you have to be very experienced where you can handle that. And if you look into like top quality power supply, all of them are switching pre-regulators. They never let you have the switching system directly touching the hardware. It will fry itself. So it's like, you have pre-regulator, it drops the voltage. Like in this scenario, I dropped 12 to 5, then 5 to 3.3, and 3.3 is the output. Same will happen in almost all pro-grade lab power supply. They will always have a switcher for efficiency, but they will never drop it to, you set it output to, let's say, 15 volts. The LDO, low dropout rate, they are more efficient. Low dropout rate, they're like, okay, I'm gonna take 15.9. So 15.9 would be created for SMPS. It will go through a lot of capacitor, lot of inductor, and lot of magnetic ferrite beads to remove all the noise content. And then it will go to linear regulator. Linear regulator is like, I got this. I'm going to flatten this puppy out. And another benefit, linear regulator can react very quickly to short circuit systems. And if you make all of this, basically what is inside these regulators, you can make it outboard also. Means every component, I say, you can respond in microseconds, not milliseconds, microsecond. You can respond like, pootum, very quickly, like kind of necessary when you are dealing with expensive spicy circuits. So that's why do not be tempted by, like, SMPS. If you want to go into SMPS, go into pre-regulator SMPS. Basically, again, this channel has a that ironically that was the first video. This is later video, but trust me, there is a reason why people want to start out with linear. You do not want the unknown, the frying systems introducing system. And this design, I like the system because it goes to 0 volt. For example, if you have any idea about LM357, no, what is this? 317, sorry, 317, this will not go to 0 volt. There are certain chips that can go to, but these are very common, very cheap, very robust. So people generally use that. It requires negative voltage, so Zener reference that is inside it can go down. And that's another benefit. If you actually expand everything like a proper linear power supply, you will not have to deal with that 0 volt issue. This does not allow you to go to 0 volt unless you have negative voltage. This design actually solves that issue. So it's actually quite useful, so to say, product. So, and it also has high current bypass. For example, this is a transistor, not a switcher. So it will just burn the voltage away. And penalty of that is just heat. It's just heat, lot of heat. So what can you do? Well, you can have a different element. That sole job is I dump the current, I endure the heat. I'm designed to endure the heat. For example, high current pass amplifier. And if you're like, okay, where the hell I'm going to get all this part unless I buy the whole kit? Yeah, buy the Chinese cheapum, basically audio amps. They will have almost everything. They will have the transformer, they will have the pass amp, and these things are not that expensive. Like you can have a very good thing. Again, if this project was cooperating with me, that would be the next project I would be building. So again, everybody starts with that, and there is a genuine reason for this. Do not be like, oh, I can make switcher. Of course you can make switcher. You just can't make them react as fast and as cleanly as this puppy. Then we come to the second problem that all of you are going to face. That is the soldering system. And if you have a bad soldering iron, like a cheap soldering iron, for example, like this, something like this. Yeah, this is bad. This is what we call gives you a headache. So now you're like, oh, I have been like, making satellites with this. Of course, I know you can. But here's the deal. You do not want to deal with this hassle of this, like, because your time is the most valuable aspect. And another aspect is because these designs are very sloppy, they actually do not have a good thermal conduction. Like, wait a minute, it's a heater. Why the heck it does not have conduction? Yeah, because it has ceramic heater, then it has air, and then you have the tip. And you know anything about air does not like to conduct heat. So this is very inefficient. So the core, the actual heater element could be very high, 400 degrees Celsius high, and the tip would barely get hot. So, and that's why when you start these things, it takes so long, like 5 to 10 minutes to heat it up. That's why people do not like these sort of things. This was a very good technology back in the vacuum tubes days, back in the days where we did not have to worry about frying the electronics. Now it's an issue because you could have a lot of sensitive circuits. Like if you fry them more than 215 degrees Celsius, yeah, they kaput, they date. So fundamentally, we are all getting fed up with this sort of cheap brain damage, and now we are all going to what we call cartridge-based system. The idea with that is your soldering station and stick is separated. Here, I'm getting 20 volt here. That is gone. You will have a separate box. That box will be the expensive box, and this will be a tip, so to say. And the benefit of this tip design is that tip itself has the heating element, and it also has the thermometer. So not only it can heat directly, it has heating element, ceramic, and the outer body shell. Nothing in between. There is no air gap. So even with 30 watt power, this puppy can bitch slap any 75 watt iron, so to say. That's why people are switching into this. Every country, every company, every mobile reparation, every laptop technician, all of them are switching to this for this exact reason. It does not need to ultra heat it so it can do some work. And again, this because of that, it also has very less chance of frying your circuits. Another aspect is because it has thermometer at the tip, it knows how much energy it requires. It's like, oh, I'm at, let's say you set it to 210 degrees Celsius. It will stay at 210. It won't be like, okay, turn it on 210. It's like, I think it's 210, let me turn it off. No, this has a meter, this has a feedback loop. That's why this sort of system is very desirable. It does not matter which brand you're looking at. There are two very popular systems. You have JBC systems, and then you have T12 systems. Now T12 systems are 24 volt 3 amp system. These are 48 volt 3 amp systems. Now again, many people over amp it. They do not fry itself, but again, JBC rated it at 3 amps, meaning you should be able to run this 24 into 7 into 365 at 3 amps. If you send it at higher, it could fatigue. So that's why you're supposed to go up in the voltage, not in amps. So fundamentally, the fact that stick itself has the heater and thermal sensor allows the job to be done very precisely. So, okay, how the heck you drive it? How the heck you build this box or these box? And you can't buy this, trust me. These things are so idiotically expensive, they do not even have a price. Like you have to go to somewhere else only to find the price. Most of the first party seller get contact us for quote. That's how expensive they are. So bonkersly expensive. So this video that I have linked on below is my personal favorite system because they are not using switching regulator, they are using transformer. Benefit, transformers are very long lasting, meaning if you treat them right, they can last for decades. You do not have to worry about too much noise from that. So transformer. Now how the heck you control the power? Well, to control the power you have a triac. Now triac is just a fancy silicon switch, so to say, and benefit of that is that if you do it right, you can switch it when it Basically, your voltage starts from 0, goes to 220, and then comes back to 0. Then it goes to minus 220, and then it goes back to 0. Now, having transformer and triac in between, you can just turn off the moment a pulse goes to 0. It's like, oh, it went to 0. I think I'm already hot enough. No worry. You let it cool down, cool down, cool down. It's like, okay, next time you just try to, and again, because it's happening 50 times a second, technically 100 hertz, as in like how many pulses you have of energy, you have 100 hertz of it. So you can literally, you can easily control it very reliably. And again, because you are not doing phase angle control, that shall never do phase angle control. It will basically, if you ever try to run it on inverters, it will roast one of those. Either itself or the system. That's why I always do what we call triac 0 volt switching. Must do 0 volt switching. So you can buy it, build it, and benefit of this is you can buy genuine handle and sticks, because the actual chemistry magic happens on the stick, and handle just makes your life much easier. So many people are like, okay, I'm going to build my station and I can't afford those stations. I'm just going to buy the sticks. You can buy them quite reliably. So you can do that. And the reason why you want to go through this hassle is simply because trust. If you are relying on your soldering iron to work, it has to work. And many of the cheap Chinesium ones, they have this weird things where they're like, either they work for a few years or they're just like fry themselves in 1 or 2 months. You cannot have that, like especially if you are depending on it. So that's why many people build this sort of things. It's just like, hey, I know what happens in this, and it could be so cheaply enough. It's like there is either triac goes away or the whole circuit, and you can just remove the whole circuit. Circuit is super cheap. Circuit is needed for measuring the temperature of the thermocouple, and then it counts how many PID cycle loops, so to say. So that's why it's trustworthy, it's serviceable, and you can repair it if something does go wrong. For example, this person is using surprisingly low voltage, high amps. You can easily go to any cheap Chinesium company that are dealing with audio amps, and it's like, hey, can you give me 48 volt transformer? Have fun. So this is another useful tool. Like, this is something that if you build, you will enjoy it. And again, you may be like, hey, I still do not like the cost of JBC handle and stick. Yeah, they are expensive. You can go back to T12, and most of the design will work. Only the amplifier circuit will change because the thermocouple is in series with the heater. So this is another useful product that people do, and they're like, hey, I'm having fun. And again, let's say you become successful enough or you make more than enough money, you have the systems. So this is another useful product. Now we come to LumenPnP. Now all of you know PNP is pick and place machine. So you have to understand, our electronics industry became mass producible because we switched from through hole components, basically components that are like this, what we call through hole, to basically surface mount, things that are mounted on the surface itself. I would recommend all of you to buy this sort of PCB rulers. They have a lot of footprints measured here, so it would be useful. So how do we manufacture it? PCB, right now there is at least 5 or 6 options you will have. Any country, even in India, you will have a lot of PCB manufacturers like, you give me the PCB, I'll give you the actual, basically give me the design file, I'll give you the PCB. Now here's like, okay, what about populating it? Yeah, that requires a different machine. That is PNP machines. Those are expensive, and they have this weird thing because of the people required to run those sort of PNP machines and the cost and all ecosystem. If you go to JSL PCB and it's like, hey, can you assemble the board for me? They're like, yeah, of course. How many pieces? You'll say like, okay, let's just do 5. They're like, bro, here to me, bro. I get it, you want it. Do it yourself, man. Trust me. We can do it for you, but trust me, do it yourself. And you're like, no, I can pay for it. It's like $5 of parts, $5 of PCB, and $500 for the assembly part. It's very bonkersly expensive, like especially on small run. If you're like, okay, I have this design, I want to make 10 pieces of it, then give it to everybody for testing and all that, you would be shocked how bad it is. 10 PCB, no problem, take it and go. 10 populated PCB, yeah, no. And again, if you know anything about anything, things do not work. That's the reality of it. Look up into any equipment that you have ever torn apart. The PCB generally will not be version 1. It will be like version 2.7, version 13.8, version 2019, version 2018. It will always have something like this, because again, it never works in first try. So you have to have a system where you can cycle through those quickly, reliably. So tada, this person was like, okay, mad enough. It is like, okay, what if I make the machine? It's like, okay, let's just make it. And you made a company with that. So fundamentally, for small run, for getting that quick iteration, and sometimes that's all you need. That's also another design aspect. What if you are making something that's so niche that at best case scenario, you're only gonna make, let's say, 10,000 of those. 10,000 is a bit much. Let's just say 500 of that, right? It's a niche equipment, only 500 people. It's not worth to go to those PCBs, go YOLO. Pick and place servicing? No. And again, what if you want to do in sequential? What if you want to build 100, then update, then do it again? Yeah, those will bankrupt you if you try to do those systems. So what is pick and place machine is just CNC with vacuum. Basically, it sucks a lot, and it requires a camera, because you have to understand, whenever you are talking about small items, tiny items like 0805, which again is big enough, 0603, ooh, that's small, 0402, ooh. If you are talking about something that small, you can't never pick it up like 90-degree, absolutely. So you pick it up with a vacuum and hope your nozzle is not clogged. And you pick it up, then you go on top of a camera scans it. It's like, okay, what is the XY coordinate and what is the rotation? Based on that, then it calculates the basically where the G code is, basically where it's supposed to go. It goes there, places it. So it's a tricky thing. It's not hard. It's just tricky, a lot of tricky things. So this person made a company also. For example, many people are like, hey, I'm cool, I'm down with it. It's just I want the damn product. He's like, okay, I made the company, buy the damn product. It's like, okay, I do not, like, let's say you are in India and importing here will make you bankrupt. You're like, okay, what if I want to build it? Everything in this is open source, meaning if you have a bit of patience, you can build it yourself. All the designs are open source. So it's really, really great for rapid prototyping in-house, because even in India, like let's say you are in Bangalore or certain metropolitans, there are PCB fabrication shop that, like, if you pay them boatload of money, they can give you PCB in 24 hours. PCB 24 hours. In China, some of them, like if you pay ultra premium, they can get you in 12 hours. So fundamentally, if you want rapid prototyping, you want this. It's like, and again, for small scale production, you can just do production. And production will not be limited. Oh, I designed the PCB. That's what it is. Like, oh, God damn it, that I could make this better. You can make this better. And if you're like, oh, what about the component cost? Components are surprisingly cheap if you buy the whole reel of it. And you can use the reel machines here. So you can get it quite reasonably priced. So it's a really unique tool where it's like, what if you just do the whole assembly? I'm just waiting for someone to figure out how to make PCB. And yes, I know you can make PCB in house, but I'm talking about something like this, like full PCB, where you have not only the traces, you have solder mask, and then you have exposed pads that are tinned, and you have holes, and then you have sill screen. All of those things have to be there. Don't just like, okay, you can etch it. Of course you can etch it. It's just like full package. I've seen one people who are working on making a laser system that can allow to do all of that, meaning through holes and etching and masking and printing and all that can be done. But I've not seen something that has reached maximum productivity yet. But this has reached. So meaning all you are waiting for is PCB, and then you can just rapidly iterate. And you're like, okay, why can't I just do it? Yeah, good luck. Especially if the board is complex enough, it's like, no, it will take 6-7 hours to do one board. And God help you if you have to do 10 of them. So that's why this is another amazing, awesome, useful tool. For rapid prototyping, it's like, bro, this should be in every university. Then we come to the God project of all, DIY scanning electron microscope. Yeah, let that sit in. Scanning electron microscope. Now, it's the biggest flex of brains and balls I have ever seen. It's like, yeah, I got brains, man. I got it. So this is the best. And I am falling back to the quote, the great Louis Rossmann. He says, like, if a person built it, you can do it too. And the fact is that it's actually true. The only difference between you and a professional is just that how much time it's going to take. And I'm not talking about healthcare or engineer, but things of this nature. You can do it. It's just that if they could do it in 1 month, it will take you 1 year to do it. If they can do it in right cost, it will take you 10 times the cost. But you can do it. Never let that stop you. It's like, again, I'm someone who studied arts, but I'm still trying to build it. And again, this is my Mark II board compared to my Mark I, which was this one. Much more, a lot of improvement happened. And I'm this close of getting a MOSFET to behave as I wanted to. I have no idea why the heck MOSFET turns on the moment power is there. And yes, I do have gate resistor and all that still turns on for a brief second. It's just like, oh, no, I have to. And that defeats the whole purpose. They're supposed to be off. But again, I'm working on it. So what is an electron microscope? All it is just an electron pew, and then you have an accelerator, and then you have condenser, lens, and then you have XY raster. Basically, you're scanning it XYZ. Basically, it's a CRT TV with extra spice. You just run it at very high vacuum, and you accelerate it to be really ludicrously fast. It's just a CRT. It's basically a CRT. You are just making it much faster. Point is much finer, and you focus it, and then you send the waves back into a phosphor glows, you have photomultiplier tube, it does the all data. Now here's the how the heck you take the data, convert it into useful 2D image, you send it to oscilloscope. So it's nothing magical, and this is the whole point of it. The fact that he actually got an image, again, it was not a like god tier or very high end, because he made it as a proof of concept. And it worked. Let that sink in. He made a proof of concept and it's like, ta-da, it works. So this is really, really amazing. And what are the spicy part here? Now you may think vacuum. Yes, vacuum is spicy if you want to use turbomolecular pump. But if you want to use your, let's say, normal HVAC refrigerators, the compressors, the vacuum pumps they have, that's more than good enough. They're like, okay, they won't go to very low vacuums. They won't. But you have old technology, as in like 1930s technology of oil pumps. You can literally have oil that can help you to remove all the remaining air molecules. So that's the whole point. If it was done in 1930, meaning all the things that were required for this is just available right now. Although there is one thing that not somehow, I know exactly, but humans went backwards. Meaning in 1930, if you ever picked up a phone, it's like, bro, I need like, let's just say, 15 kilovolts power supply that is regulated. And again, I'm talking microamps, not like milliamps or kiloamps. It's not your transmission line, but voltage is high enough. I want that high voltage, but I want regulation, as in like not just a flyback circuit that's going no, like actual regulated 11 kV. Yeah, we used to make them, lot of them. Like, why? Well, you seen neon signs? Yeah, they used to be very high voltage, very current limited. So that was a very big circuit. A lot of vacuum tubes, not every, but a lot of vacuum tubes also had some weird requirements like 500 volts, 800 volts, 1500 volts, 9 kilovolts. So back in those days, if you picked up a phone and wanted a power supply that can handle this sort of bonkers high voltage, they're like, yeah, we have it. And right now, if you go into any modern one, some of those puppies can go up to 40 kilovolts. Again, let that be like, a current is minuscule, but it is serious. It's a serious puppy. Now, based on this system, this gentleman, this is soldier gentleman, he just got a bit excited and he's like, let me build it. So basically this was Mark 1 prototype and this is Mark 2 prototype. And this makes me lose hope in myself. It's like, what the hell am I doing? This guy literally takes a puff board and makes a motherboard on it. And I'm like pooping myself trying to make a MOSFET work. But again, that's why I'm not showing this. Again, the video link is down below, but it's like, what the hell? And again, I think it will take another 5-6 months when he has fully ready and finished. And because he's digitizing it, here everything was analog. Everything was analog. You can just trust it. Here it was like they're trying to digitize it. Benefit is that you will be able to refine it, meaning this could not actually zoom in too much. It was just like, yeah, it's an electron microscope, but it's like proof of concept rather than, oh, this is an electron microscope. I can see that there is no color in a butterfly wing. That was not there. This should be able to do that simply because every part is tunable. Again, digital does give you a lot of complexity, but benefit is repeatability, meaning you can repeat it. Oh, this exactly what happened. So this is the most amazing project I have seen so far. Usability wise low, but like, again, I really wish this sort of system became just like, oh, if you are going into college or university, just like they have an open source project for this, everybody's building it. It's like, yeah, it should not be like, and again, I get it, like those transmission electron microscopes, those are bonkersly expensive. And the truly, really, really, like if you want to read 10 nanometers or 15 nanometers, something that small, yeah, you need like professional grade system. Although professional grade systems are made by professionals, so professionals are trained in colleges, they can make it. It's just really tedious. So make a basic one. Everybody works on it, refine it, make it cheap enough and all that. And then you're like, no, we really need some serious oomph. Okay, then you upgrade the power rails from 10 kilovolts to 40 kilovolts and other associate things. But it is doable. It is doable. That's the whole point of this. It is doable. You can do it. If humanity figured this puppy out in 1930s, you can do it too. Again, it will take longer and it will cost a lot of money, but it is doable. So this was my presentation on basically the best DIY projects I have seen so far. If you are interested, please ask me. I'll make part 2 also. I hope you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.